Unit 1-2. Unit 1-2, segments, raise, and distance. Segments, raise, and distance. And what we're doing here is we're talking about parts of a line. If we had a line with 2 points on it, like line AB, the way we name the entire line is arrows on both ends and then AB. If we only wanted a segment, then we would start at A and stop at B and have all the points in between. Now, geometry book definitions are telling us how to draw it. So here's what the real geometry book definition says uh, uh, as far as the definition of a segment. It says it is the part of line AB that contains point A and point B and all of the points on line AB that lie between point A and point B. And so you can see that the definition takes that little piece out of the line. It's the part of line AB that contains point A and point B and all the points on line AB that lie between point A and point B. Now, it suffices for me to say that it starts at point A and stops at point B. Starts at point A and stops at point B. Sometimes on a segment we put little dots to represent starts at point A. Let me regain my things I just lost on the board there. Starts at point A, stops at point B. We generally name a segment, though, in geometry without the little dots for the endpoints, but we're still saying as we read this, we would say for this one, go infinitely through point A and point B. We would say here, starts at point A and stops at point B, whether it contains those little dots or not. So the symbol for a segment is just that, segment AB. Now, if we think about segment AB on this line, point A, point B, and point C, where point B lies between point A and point C, point A, B, and C on the same line where point B lies between point A and point C, we could conclude that AB plus BC would then be the whole thing AC. Visually and with numbers, if this is 3 and that's 4, then you could say the whole thing AC was 7. We call the fact that segment AB, that's from here to here, plus segment BC is equal to the whole thing segment AC, we call that segment addition. Now, that's a postulate. That's the second postulate of geometry. Our first one was the fact that the intersection of two planes is a line. So postulate 2 geometry is segment addition. And let's kind of blow that up so it gets our attention a little better. If there exists a line with 3 points on that line, such as point A, B, and C, where B lies between A and C, then we can say that segment AB, the first little piece there, plus segment BC, the second little piece, is equal to the whole thing segment AC, and we call that segment addition. Segment addition. So we have a little postulate inserted there in fine print. Now, remember we said the line went indefinitely through point A and point B. The segment started at point A and stopped at point B. If we think about ray A, B, then it starts at one point and goes infinitely through another. So it would be the part of line A, B that starts at point A and goes infinitely through point B. Starts at point A and goes infinitely through point B. Notice that on array, the endpoint was named first. Ray AB would have the endpoint to start with and the point it goes infinitely through later. We would not call this ray BA. You can't write array backwards like you can a segment from either endpoint. Okay, so that's a incorrect way to write a ray. The ray symbol always faces to the right. The arrow always faces to the right, meaning that the endpoint is always the starting point, the one named first, the one to the left, as we name the ray. So if we think about the ray that starts at point A and goes infinitely through point C, we would call that ray AC. We could have also called that same ray AB, because whether we go infinitely through B or infinitely through C, we still went infinitely through the right as we started from the end point, point A. Now, if we wanted to talk about the ray that started at B and went infinitely through A, we still have to make our ray symbol, our arrow to the right, even though in the picture it's going to the left. We named the end point first, so the B would go first, and the point that it goes infinitely through would be named second. If we talk about ray BC, we're still going to name the ray to the right. We do every single time. The starting point of that ray is B, and it goes first, and then it goes indefinitely through C, so the C goes second. So we name a ray with the arrow always facing right, with the end point first and another point on the ray in the direction that the ray is going second. Now, opposite rays. Opposite rays are two rays that have a common endpoint and go in opposite directions. So opposite rays would come from a line, or they would form a line. And so if I have a point B somewhere, and there's a ray that goes to the left from point B on a line, and a ray that goes to the right of B, and I did that backwards, I know, to the left and to the right. From point B, we call those opposite rays. So opposite rays are rays that have a common end point. Have a common end point and go in opposite directions. So an example of opposite rays, if we look at this example, if we started at B and went in opposite directions, we would have ray BA and ray B, C, or D, right? We could call that one ray BC or ray BD. If we started with point C, we could say, well, we could go opposite directions from C. So we could have ray CB to the left and ray CD to the right. So there's two pairs of opposite rays that we could name. You might also take note that this ray CB could have also been called ray CA because A is also a point to the left, okay? Opposite rays are two rays that have a common endpoint. There's an E on opposite rays there, opposite directions, and going opposite directions, okay? Now, here's what we've looked at so far. We said this symbol means line AB, which means it goes infinitely through point A and infinitely through point B, hence the arrows. And segment AB would start at point A and stop at point B. It's the part of line AB that contains point A and point B, and all the points that lie on line AB between point A and point B. Ray AB would be the part of line AB that starts at point A and goes indefinitely through point B. And then opposite rays are two rays with a common endpoint that go in opposite directions. And then we come to the symbolism of AB with nothing above it. Now, AB with nothing above it means distance. It means how far is it between A and B. In other words, how long is segment AB? So the length of AB, denoted AB, means the distance between point A and point B. And if you recall back in your mind in the Algebra 1 book that I wrote on page 177, we dealt with the ruler postulate. We dealt with the distance formula, the midpoint formula, Pythagorean theorem, and this is really the ruler postulate. The ruler postulate is postulate 1-3 of geometry. The distance between 2 points on a number line can be found by taking the absolute value. You remember that? That's actually on page 88 of the algebra book. And when we're talking about absolute value, don't forget that we're talking about distance from 0 on the number line. So we could say the absolute value of -2 is 2 because it is 2 units from 0. And the absolute value of +2 is 2 because it's also 2 units from 0 on the number line. The ruler postulate, or the formula for the distance between 2 points on a number line, is the absolute value, that's those bars, the absolute value of the difference of the coordinates of the 2 points. So we would take the coordinate of A and the coordinate of B. So we take the absolute value of the coordinate of A, which is -2, minus the coordinate of B, which is 1. -2 minus 1 is -3. Sign rules are on page 18 of the Algebra 1 text if you'd like to refer back to your sign rules. The 1 and 2 are both negative. When you add or subtract with the same sign, you add and take the common sign -3. Absolute value represents distance from 0, and -3 is 3 units from 0 on the coordinate plane. In other words, the absolute value of -3 is a +3. And so the length of segment AB would be 3. If we wanted the distance between A and C, the coordinate of A is at -2 and the coordinate of C is 3. So we would have the absolute value of the difference of the coordinates of A and C, A being at -2 and C being at 3. So we have 2 minus 3, which is absolute value -5. Absolute value can't be negative. It actually represents distance from 0, which would be 5. And so the length of segment AC, denoted AC, would be 5. Any questions on postulate 1-3, which we know as the ruler postulate from geometry and from algebra? Page 177 of my algebra book, and then absolute value, page 88 of the algebra book, sign rules, page 18 of the algebra book. So there's places to go refreshing those skills if you need those. Congruent. Now I want to get into some symbols. I want to talk about some symbols that we may need. So we're going to talk about this symbol and this symbol and this symbol, this symbol, this symbol, and this symbol. First of all, I want to talk about this symbol versus this symbol versus this symbol. In the English language, we read from left to right. So when you read this, you're going to read into the big end. Notice it has a big end and a little end. When you read into the big part, you would say big or bigger or greater than. Greater than. If you read into the little end rather than the big end, you would say smaller or less than. If you look at this, it's the same size on both ends, so it's not greater or smaller. The two things are considered equal. And another name for equal would be, another concept would be same size. Now, in the Algebra 1 textbook on page 57, we talked about similar triangles, and we said that similar triangles are triangles that are the same shape, and we gave it that little squiggly symbol. That is the symbol for similar, and similar means same shape. And we said from page 57 of the algebra text that if two triangles are similar, then corresponding angles are equal and corresponding sides are in proportion. So similar figures are two figures that are the same shape, not necessarily the same size. So we talked about scale factor. We either scaled up or scaled down, dilated up or dilated down. And so we need to know those definitions. And then when we look at this symbol right here, this symbol has an equal sign and a similar sign. The equal sign part means same size. The squiggly part, that similar part, means same shape. And so when you put those together, you get same size, same shape. So congruent means same size and same shape. Now, all segments have the same shape. So to be congruent, they would obviously just need to be the same size. So congruent, what would make them the same size would be their length. Remember, we talked about that dimension of length, width, and height. And so what would make segments congruent would be the fact that they have equal lengths. So if segment AB has a length of 3 and segment CD has a length of 3, we could say that segment AB and segment CD are congruent, or we could say that segment AB is congruent to segment CD, and you can notice the symbolism there. AB congruent to CD. Midpoint. Well, here again, the very word defines itself, mid point, and you could say, well, that's point in the middle, but see, that's not really quite enough, because in geometry we don't want to just know locality what it is, we want to know really what it does. What do we get out of it, in other words? Well, if we were to get the midpoint of this segment AB, then that would be a point that specifically did something for us and gave us a certain outcome. It would be that point that divided that segment AB into two equal segments, segment AM and segment BM. And so the proper definition of a midpoint is that point that did what? Divided that segment into two equal segments. The point that divides a segment into two equal segments. Now, we're getting into a huge part of geometry, which is the beginning of proofs. And I try to be very specific as I make definitions and as I memorize my definitions, and try to specifically teach some things as we go so that we can actually be able to do proofs. And so it's very important that you begin early memorizing these geometry terms and memorizing things like, given that something is true, like M is the midpoint of AB, what can I conclude about that fact? Well, I can conclude by the definition of a midpoint that it's the point that divides a segment into two equal segments. So what do we get out of a midpoint? Two equal or two congruent segments. So given that M is the midpoint of AB, I can reach the conclusion that segment AM is congruent to segment MB or BM with the reason definition of a midpoint. Now, what did we have that allowed us to reach the conclusion or to give the reason definition of? This is a very important thing to start connecting to. To be able to say definition of a certain word like midpoint, we need two things. We need the word itself and the what we get out of it. Now, I know that sounds kind of funny. But notice, we were given the word midpoint, and we said, well, what do we get out of a midpoint? Well, we get two congruent segments. So we have the word midpoint, the what we get out of it, two equal segments. Since we have those two statements, we can use the reason definition of a midpoint. We use definition of as a reason in a mathematical proof when we have the word we're talking about, like midpoint, and the what we get out of that definition, two equal pieces. The word and what you get out of it. So we say definition of. You're going to hear that said several times. Okay? All right. Bisector of a segment. Now, the midpoint of a segment is the point that divides a segment into two equal segments. It's the location of the division. A bisector is an object that hit it right there and split it in two, basically. Now, things that could actually hit the midpoint would be segments or rays or lines or planes. So the formal definition of a bisector is a line, segment, ray, or plane that intersects a segment at its midpoint. A line, segment, ray, or plane that intersects a segment at its midpoint. It's an object that divided it into two equal segments. Now, so the definition we're going to give it is a thing, that thing being a line, segment, ray, or plane, that intersects a segment at its midpoint, but more importantly, when it hits the midpoint, what happened? Well, it divided it into two equal segments. So a thing that divides a segment into two equal segments. And I give it this definition because we really want the word and what we get out of it. What do we really get out of a bisector? We don't really get a midpoint out of a bisector. The bisector hit the midpoint. What we get out of a bisector is the same thing we got out of a midpoint. We get two equal pieces. So if we're given that segment AM bisects segment BC, we can reach the conclusion that segment BM is equal to segment MC. Segment BM is equal to, now I use in this text equal rather than congruent for segments and angles because I assume that people know that segments are the same shape. And that's the way I was taught geometry years ago, and in the more modern textbooks they use congruent all the time. But again, congruent segments have equal lengths, and segment's going to look like a segment's going to look like a segment. Anyway, what is it that we get out of a bisector of a segment? Well, we get two equal segments. So if we have the word bisector of a segment and the what we get out of it, we can say, given that this is true, that it's a bisector, we can reach the conclusion that this is true, we have two equal segments, and justify that conclusion with the reason definition of the bisector of a segment And we can use that reason because here's the word bisector of a segment, and there's the what you get out of it. So we use the reason definition of when we have the word and what you get out of it. Okay, so that's lesson 1, 2. Shortly we will record the